Example 4 on the work chapter. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. Okay, first off, when you're doing a spring problem, it'll have the word spring in it, so it makes it a spring problem. Okay, they're going to tell you how much force is required to hold the spring in place. That allows us to find the constant, the spring constant for that specific spring. Different springs have different spring constants. One that's got a thicker metal to it's going to have a bigger spring constant. Something with a thinner metal has a smaller spring constant. That's just how much pull the spring actually has. And the force is going to be in pounds or newtons. And it's going to use the words natural length. And that's important. So knowing what the natural length is important. So every spring has a natural length. You just set the spring down. It's not being pulled whatsoever. You measure it. That's the natural length of the spring. And then if you stretch it, now it's longer than its natural length. All right. If the force is given in newtons, you want to have distances in meters. Newton meters, right? If the force is in pounds, you want the distances to be in feet. With that being said, distances are usually given in centimeters and inches on these problems because the spring constant is for small distances only. You're not going to stretch a spring with its natural length is 10 centimeters, 25 meters long. And then the spring gets all like just bowed out and it doesn't work anymore, right? So we're working on short distances here. So they typically give you the distances in centimeters. We're going to have to convert to meters, all right? So the first thing we want to do is we want to take that first sentence to establish the spring constant. And Hooke's law states that if you have a spring, the force required to hold a spring is equal to its spring constant times how far it's been stretched. Very basic formula, but that's what it is. K is the spring constant, X is how far you stretched it, and F of X is the force. Right? So if we take a look at what happened here, we went from 10 centimeters to 15 centimeters. That's a 5 centimeter stretch, right? If we divide that by 100, that's 0.05 meters. And again, that's the key number there. We want meters, not centimeters, when we're dealing with newtons. And again, we want feet, not inches, when we're dealing with pounds. If you get a repeating decimal on a pound problem, give me fractions rather than repeating decimals. They're more accurate. All right, so the amount we stretched is 0.05 meters, and the force required is 40 newtons. So 40 newtons of force is required to have some spring constant stretch 0.05 meters. So every single problem that involves a spring, they're going to give you how much force is required to stretch it. That force equals K times how far we stretched it in the correct unit. Meters if it's newtons, inches, or feet if it's pounds. Then we divide by 0.05. 40 divided by 0.05 equals 800. Spring constant is what it is. So 800 is reasonable. I think I've seen one go as high as 3,000 or 4,000 before. It is what it is. It's usually something kind of like that. Next, once I know what K equals, now my F of X for this specific spring is just whatever that spring constant is times X. That's the force equation for this specific spring. So if I want to know how much work has been accomplished by this spring, then I'm going to create an integral integrating that force function over X. And what's going to go here is how far away we are from the natural position. So the question asks me how much work is done in stretching the spring from 15 centimeters to 18 centimeters. Okay, what's the natural length of this spring? 10. All right, so we know 15 centimeters is 5 centimeters beyond the natural length. 18 centimeters is 8 centimeters beyond the natural length. I want each of those to be in meters, not centimeters, right? So we're starting at a low value of 0.05, and we're coming up to a high value of 0.08. That's how you construct the integral. Then it's just a matter of evaluating that integral. Okay. Let me say one thing that's going to happen on these problems in the homework because I didn't get an example problem that looks like this. Some of these problems are going to tell you the work, but they're not going to tell you one of these numbers. If they happen to do that, W's work, all right, let's say 0.05 up to x. All right, so you put the number there, you put 0.5 there, you put x there, you evaluate the integral, you'll be left with an equation containing x in it. Solve for x at that point. So that's going to happen on at least one of the homework problems, so just be aware of that. But in this case, we don't know the work, so it's just everything's over on this side. Then it's just a matter of evaluating this integral. 800x is going to be 800x squared over 2, which is 400x squared. 0.05 up to 0.08. So the work is going to be 400 times 0.08 squared minus 400 times 0.05 squared. My calculator can evaluate that for me. 400 times 0.08 squared minus 400 times 0.05 squared comes out to 1.56. Now, when we're dealing with forces in newtons, right, and distances in meters, what kind of unit do we get on work? Joules. Joules. 1.56 joules would be the correct answer there. If we're dealing with pounds and feet, we're going to get foot-pounds. Newton meters is joules.